Okay, so picking up where we just left off, we were finishing that last boundary, the boundary of segment AB, combining all like terms here as we expand everything that once we substitute y equals 9 minus x into the original function, we're going to be left with negative 61 plus 18x minus 2x squared. And again, we can take a derivative. Right now, everything is with respect to x. We would see very quickly that 18 minus 4x would be what we'd have. Letting this equal 0 and solving very, very quickly, we could see 4x is equal to 18. That is, x would be 9 over 2. That would be a critical number for this function f as it's written with respect to x. To find out what y is, well, y is 9 minus x. 9 minus 9 over 2, well, 9 over 2 is 4.5. Well, you get 4.5 as well. So we have this point 9 over 2 comma 9 over 2, and f of 9 over 2 comma 9 over 2, you could substitute 9 halves in for x and for y into the original function. I'll leave that for you to do very quickly. You'd get negative 41 over 2. Now, as we said before, as we look at segment AB, the endpoints at x of 0 and y equals 9, and then x equals 9 and y equals 0, were already taken care of in the previous two boundaries. So, what we've got here is we've optimized this function as y was equal to 9 minus x. You can see there's just this one point that we're dealing with. So look, we go back to our three boundaries. I've circled all the boundaries there. We go back to our critical point of 1 comma 1. We saw that we had a z value of 4 or a function value of 4. So now we can talk about absolute max, absolute mins. Look at all these z values. The largest you'd see is at 4. The absolute max of 4 at the point 1 comma 1. In other words, you'd have the ordered triple 1 comma 1 comma 4 being the highest point on this surface. Take a look at your absolute min. Well, your absolute min, you've got to find the smallest z value that you ever can achieve. I hope it's pretty evident that we're seeing that occur here at negative 61. So we'd say the absolute min of negative 61 at two ordered pairs of 0 comma 9 and 9 comma 0. So this is really what we're doing for a final answer. I circled all those other ones to just help us realize that these are extreme values. We just have to find the absolute max, the absolute min. So again, what you do is you do what we have been doing. Find your critical numbers in a given region. Find out what that z value is. And then the bulk of the work is going to be working with these boundaries. And as we work with the boundaries, we're going to have some new potential extreme values. Let's take a look at number 2 on the back. Just very, very quickly, stating the obvious, we're going to have a new kind of region, a rectangle. And you can see that they're telling us that we're going to be optimizing. We're going to find an absolute max or an absolute min when x is between 0 and 3, when y is between 0 and 2. So we've got this rectangle right here. Obviously, we could have segment OA, segment OB, and segment BC and segment AC as well. And hopefully you can see that our region, even our critical numbers, must be within these parameters. What happens if a critical number shows up but it is not between x values between 0 and 3 and y between 0 and 2? Well, we're not going to investigate that. So that's first and foremost. Let's see what we did. We first wanted to just go back to our function and take our partial derivative of f with respect to x. Let's do that real fast. We'd get 2x minus 2y. And of course the 2y itself is going to cancel out to a 0. With f sub y, derivative of f with respect to y, well, we'll be left with, let's see, a negative 2x and then plus 2. Negative 2x plus 2. So hopefully we agree with that. Setting both of these equal to 0 will get us a system of equations that we need to solve. But happily, as we look at the f sub y, I think you can quickly see that x would have to equal 1. And if x was equal to 1, I could substitute that in here and say 0 would equal 2 times 1, which is 2, minus 2y. We'll add a 2y to the other side. Y itself would equal 1. So I have this ordered pair of 1, 1 on the interior. Very importantly, that will be investigated. We are going to look at that. So I've got 1, 1. Let's evaluate what happens at f of 1, 1. Again, I don't have to use that second derivatives test. Well, plugging in 1's up to our function, I think you could hopefully see that we'd have a 1 minus 2 plus 2. So the negative 2 and the 2 cancel out, and we'd just be left with a 1 itself. Well, what next? Well, we've got 4 different boundaries to consider. My goodness, this could take some time, but let's talk about it all the same. So, look, we'll have a boundary of, let's start at OA, perhaps. With OA, that's going to occur where x is equal to 0. Where x is equal to 0. Very quickly, what happens is f, look at this original function. If x is equal to 0, you're left very simply with f is just equal to 2y. Now, amazingly, we need to talk about this. As we take our derivative of f with respect to y, so very often kids will wonder, they'll say, wait a minute, that's just a 2, and 2 is never equal to 0. And that means, guys, we don't have a critical value, a critical y number in this parameter. We'll just check the endpoints. Look, on segment OA, what we have very quickly would just be endpoints of 0, 0. And of course, this is occurring for y being greater than or equal to 0 and less than or equal to 2. So really what we're looking at is saying investigate the points 0, 0 and also the point 0, 2. Now we could, if we were very clever, just substitute that into our f equals 2y, because we already simplified x equals 0 in there. We'd see that f of 0, 0 is 0. We'd see very quickly that f of 0, 2 is going to be a 4. So look at this. We have some potential values of 0 and 4 here. Perhaps those will be absolute mins and maxes. It remains to be seen. What else can we look at? Well, we could have the boundary where perhaps you'd like to investigate what's happening at AC. What happens when we have AC? Well, at AC, that's the line y equals 2. AC is the line y equals 2. So plug in y equals 2 into your function. And I hope it's not going to be too much of a stretch for you to see that when y is equal to 2, we have a parabola, x squared minus 4x plus 4. By the way, we also have x values between 0 and 3. As we're looking at AC, guys, I hope it's pretty clear we have endpoints of 0, 2 and also 3, 2 as well. So we're going to have those endpoints. But very quickly, let's take a derivative and just see if there might just be some possible other values on that segment that we might need to investigate. You will see that there are. We have 2x minus 4. If I were to set that equal to 0, I hope you can quickly solve even by inspection and see x is equal to 2. Of course, y is equal to 2 on this line also. So do you know what we really have? We have our endpoints on segment AC. We've got 0, 2. We also have this point in the middle, 2, 2, on that green segment. And then don't forget we've got 3, 2 as well. So from here, and by the way, 0, 2, very often kids will say, well, why do we need to even write that down? Isn't that in our previous checkpoint? You know what? It is. If you look back at boundary of A, 0, 2 we already represented. So real quickly, let's just figure out what's happening at f of 2, 2 and f of 3, 2 and see what we get. Well, very quickly, if I were to plug in 2, 2, 2 squared is a 4, and 2 times 2 times 2 would be an 8. 3 2's multiplied together would be an 8. And then 2 times 2 right here would be another 4. 4 minus 8 plus 4, you can see, is 0. So wow, we've got another ordered pair of 2, 2 that gives a z value of 0. What about 3, 2? Well, let's investigate what would happen there. 3 squared is 9. And 2 times 3 times 2 would get you a 12. 3 times 2 is 6. 6 times 2 is 12. 2 times 2 is a 4. So we'd get 9 plus 4 is 13. 13 minus 12 is a 1. So here are some other values that we can consider. Let's see. Well, we had boundary AC. How about we take a look at the boundary on BC? Boundary for BC is right here. You might wonder, well, what line is that? That's the line x equals 3. X is equal to 3. So, look, I'm going to scroll down just a little bit. So we've got the boundary at BC. That's x equals 3. Let's see what we've got. Take a quick look up here. If x is equal to 3, 3 squared is 9. 3 times 2 is 6. That's a 6y. Well, my goodness, look at this. You would have 9 minus 6y plus 2y. That's 9 minus 4y. So our function is 9 minus 4y. Well, again, you can say, are there endpoints? Yeah, there are. Let's see what happens, though, as we just take a derivative and say, wow, if my function is 9 minus 4y, taking a derivative with respect to y, you just get negative 4. And guys, there's no critical value of y that we need to investigate. We just have to look at endpoints on BC. And one of them we just did. We did 3, 2. 3, 2 is up here. What's the one corner point that we haven't talked about on BC? 3, 0. So I'm going to investigate what's happening at 3, 0. Let's find out. Let x equal 3. Let y equal 0. We're going to come back up here. Well, my goodness, if x is equal to 3, we get 3 squared. If y is equal to 0, though, my goodness, this 2xy and 2y cancel out. You're just going to be left with a 9. So this right now, as you can look at all of our z values, we've got the largest z value so far that we see. That's a 9. Well, there's one more boundary that we're going to have to investigate. You can see there were 4 sides to the rectangle, and very quickly we can see it's OB. OB, we're going to have y equals 0. Guys, if you let y equal 0 up here, you can see you're left with f of x is equal to x squared. So f is equal to x squared. Look, we can say df dx. Real quickly, we get 2x. Set that equal to 0. You'd say x is equal to 0 itself. But you know what? If x is 0 and y is 0, we're back at the origin. We already talked about that. That's 0, 0. You look at boundary of OA. We already did that. So we've dealt with that point 0, 0 up here. We don't have to look at it a second time. What else on this segment? Well, we just have 2 endpoints, 3, 0, and 0, 0. Both of these have already been dealt with. There are no additional kinds of points to consider. So look, all I have to do super fast is say that we've got an absolute max of 9 at 3, 0, absolute min of 0, min of 0 at 2, 2, and 0, 0.